Alright, this lecture is going to be on the origins of modern astronomy. We're going to be looking at the science of astronomy and how it's evolved over time. It all started with the observation that people began looking at the sky. For centuries, even today, historians and archaeologists have been puzzled over the mysteries of Stonehenge. This is just an example we can start with. A prehistoric monument that took nearly 1,500 years to build. It's located in southern England. It's got this concentric ring of stone that create this feature that we try to determine what it is. Was it a burial site, a Roman camp, a spiritual center, a solar worshipping site, a lunar cycle map, or an astronomical observatory? Well, this is a great unsolved mystery, but no less, this feature was built as social structures and civilization was becoming more sophisticated. So, ancient astronomy. Astronomy began long before recorded history, over 5,000 years ago, when humans began to track the motions of celestial objects, so they knew when to plant their crops, prepare to hunt migrating herds, and to live with changing seasons and days. The ancient Chinese, Egyptians, and Babylonians are well known for their record keeping. In 1054 AD, the Chinese recorded the sudden appearance of a guest star. That's the scattered remains of a supernova. It's a star explosion. And this is a picture of the Crab Nebula taken from the Hubble Space Telescope. Now, they wouldn't have seen it this clearly, but they noticed that the guest star went through its supernova phase. It went from a very faint star in the night sky to being increasing in its brightness as it went through the phase of supernova. So when looking at the night sky, historical observers would have seen that all of the night sky seems to be rotating around when we don't feel the Earth rotating itself. It would have been, the night sky would have been revolving around kind of a fixed point. We would call this Polaris here, the North Star. And this is what we can see when we kind of time-lapse take pictures of it. And here's a different location. Here's, I think this is in Hawaii. I didn't look at the cities here. But we would see it, we would see the stars moving as we would feel like we are fixed in place. This then entered the Golden Age of Astronomy. This took place, and this was centered in Greece. The early Greeks explained astronomy primarily through philosophy, while using observational data to support the philosophy. The early Greeks held a geocentric view of the universe, which shows the Earth as the center. They thought that everything moved around the Earth, and that the stars and planets were fixed on a transparent, hollow celestial sphere. They rejected the idea that the Earth itself was rotating. And here we see Aristotle's universe. We see his model here, that the Earth is this geocentric version of everything moved around the Earth itself. That's how they observed it, right? They would have seen these features in the night sky. So their best supporting evidence would have been like, well, let's fit the model to reflect what we see. So Aristotle concluded that the Earth is spherical because it casts a curved shadow when it eclipses the moon. But this idea was lost during the Middle Ages as the Earth was believed to be flat. Proof of the Earth's rotation did not come until 1851, if you can believe it. Well, what happened in 1851? How do we know the Earth rotates? Well, observe a pendulum's motion, right? It just swings back and forth. But a pendulum will oscillate back and forth rhythmically. In 1851, a scientist named Foucault used a pendulum to show that the pendulum swings vary over time as the Earth rotates beneath it, thus changing the path of the pendulum. Eventually, the pendulum swings go back to its original position, and this depends on which latitude you're swinging it at. But this showed for the first time that the Earth was rotating. So this pendulum knocks down these little metallic pieces as it changes its path. It would have started off here. These have been knocked down, and it swings differently over time. Now, that picture here. And you can watch this little video here. It's actually showing them knocking down this Foucault pendulum, knocking these little steel pieces down over time. So it's a time-lapse video that somebody created on their own. So another historical scientist, a Greek astronomer, in 240 BC, named Eratosthenes, made the first good measurements of the size of the Earth, where he compared the shadows of two nearby cities and noted how the shadows differed during the summer solstice. His basic knowledge of geometry and knowing the distance between the two cities of Alexandria and Syene were able to help him make a remarkably accurate calculation of the circumference of the Earth. So he compared the shadows in a well in which of the city he lived, in Alexandria, to Syene, a city that was further south. On the summer solstice, sunlight did not reach the bottom of his local well, so he concluded that the sun was not directly overhead. On the same date in Syene, the bottom of the well was receiving sunlight, proving that the sun was directly overhead. So he knew the sun was never directly overhead, even on the summer solstice, in his home city of Alexandria, which is further north than Syene. He realized that he could determine how far away directly overhead the sun was in Alexandria by measuring the angle formed by the shadow from a vertical object. So he measured the length of the shadow of the tower in Alexandria, and he used simple geometry to calculate the angle between the shadow and the vertical tower, and this angle turned out to be 7.2 degrees. Next, he used a little bit more geometry to reason that the sun's shadow should be the same angle between Alexandria and Syene as measured from the Earth's center. Conveniently, 7.2 degrees is 1/50th of a full circle. So Eratosthenes then understood that he could determine the distance between Alexandria and Syene. He would merely have to multiply the distance by 50 to find the circumference of the Earth, which solved to be about 24,000 miles, which is relatively close to 25,000 mile circumference of the Earth. Well, that view then began to change into the heliocentric or heliocentricity, started preparing the humans for a sun-centered universe. So Aristarchus was the first Greek to profess a sun-centered or heliocentric universe. He used geometric relations to calculate the relative distance from the Earth to the sun and the moon. Although much of his math was wrong, it was way too small, he showed that the sun was many times more distant than the moon, and the sun was many times larger than the Earth. And even so, now he began to use math and create these models. Now he started taking humankind and civilization to a greater distance in the scientific world, but geocentrism, this ideology, prevailed. So Ptolemy, then enter Ptolemy's model. Ptolemy's major contribution that his model could so accurately explain the motions of heavenly bodies, it became a model for understanding the structure of the solar system. There were tremendous and complex social and religious implications for the geocentric model versus the heliocentric model of the universe. Most of the early models showed the Earth was the center. It was not only the center of the solar system, but of the universe as a whole. The Ptolemaic model accounted for apparent motions of the planets in a very direct way. It assumed the planets moved on a small sphere called an epicycle. Notice we start getting smaller circular motions mixed in with larger circular motions. So it is the stars, it assumed, moved on a celestial sphere on the outside of planetary spheres. And this model was not challenged by society for over 1,300 years. That's 1,300 years. Very remarkable how long that kind of led the science in the astronomical world to just stay static, that nobody challenged it. Then enter retrograde motion, the backwards drifting. Sometimes a planet appears to change its direction in the sky as observing them from Earth. This retrograde motion is entirely an illusion caused by the Earth moving slower than outer planets. Typically, planets move towards the west in the night sky viewed against the backdrop of the stars. From time to time, they change direction and move eastward before returning to the westward motion. Well, this is the illusion caused by the Earth's motion being slower than the orbiting object being observed. So we would view something as moving in one direction and then travel back and retrograde and then continue before resuming its original path. So let's envision that. So when you pass a car on a highway, you may approach a slower car. It is clearly moving in the same direction as you. Right as you pull alongside and pass it, the car appears to move backwards just for a moment before you view it moving forward again. This is the perception of retrograde motion. In the picture, we can see how Mars, which is further than the Earth, right, a greater distance, it's 1.5 AUs from the Sun, moves in retrograde motion, perceived as temporarily reversing its motion. So as it's orbiting, we would view it, even though it's moving in this general direction, here at this location, it's actually going to be having this retrograde motion because it's traveling at a different velocity. Now comes the birth of modern astronomy. Nicholas Copernicus revisited Aristarchus' work. Copernicus became convinced that the Earth is a planet just like the other 5 known planets at the time. Observations were better fit from a rotating Earth, and retrograde motion is further explained in greater detail, accounting for our perception of retrograde motion. So Copernicus was the first to state that the Sun was merely the center of our solar system and not the universe. So he changed this heliocentric of the universe to the heliocentric of just our solar system. So the model changed. By 1508, Copernicus began developing his own celestial model, a heliocentric planetary system, not a universe. He showed that not only the Sun was the center of the solar system, but it illustrated that the planetary distance of the Sun influenced the size and the greater time of the planet's orbit of the Sun. Well, this paved the way or primed the future for scientists coming up. Enter Tycho Brahe. He moved science further. Brahe designed a scientific tool prior to the telescope called the pointer. He did not believe the Copernican model because he was unable to observe the apparent shift in stars that should result if the Earth traveled around the sun. His argument went like this: if the Earth orbits the sun, the position of a nearby star when observed from two locations in Earth's orbit, 6 months apart, should shift with respect to the more distant stars. Well, the apparent shift is actually called stellar parallax, and it is used today to measure distances to nearby stars. It's easy to visualize. Close one eye with your index finger pointed up. Use your one eye to line up the finger with a distant object. Now move your finger and view the object with your other eye, without moving your finger, and notice the object's position appears to change. The further you are away you hold your finger, the less object's position seems to shift. And you can check out this picture here. It's showing stellar parallax. Now we enter Johannes Kepler. As Copernicus ushered out the old astronomy, Kepler ushered in new astronomy. Armed with Tycho Brahe's work, his data, a good mathematical mind and a strong belief in Tycho's work, Kepler derived 3 basic laws of planetary motion. The first 2 laws resulted from his inability to fit Tycho's observations of Mars to a circular orbit. So he searched for another solution. This endeavor led him to believe that the orbit of Mars was not a perfect circle, but slightly elliptical. He realized that the orbital speed of Mars varies in a predictable way. As it approaches the sun, it actually speeds up, and as it moves away, it slows down. So in 1609, Kepler proposed the 2 laws. The path of each planet around the sun is elliptical, with the sun at a focus. And 2, each planet covers an equal area in equal time intervals. In other words, area 1 is the equal area of area 2. So therefore, if it traveled from P1 to P2, and that's a greater distance, in the same amount of time to travel from P3 to P4, it must have a greater linear speed at this location. And thus, it actually does. In order to keep the law of equal areas, his second law, consistent, its linear speed must change. Now, what is an ellipse? Now, you can pause this and kind of take notes on here. You will be expected to know how to do this. But we're really comparing the semi-major axis to the semi-minor axis. And we can come up with a ratio that's going to provide us, that's going to determine how eccentric the orbit is, meaning how elliptical is this. The closer that the 2 foci are together, the more perfect the circle. Therefore, the greater they get apart, the more elliptical, or what we call eccentric, the orbit. So, Kepler's third law of planetary motion. Kepler's third law of planetary motion shows that the orbital speeds of planets and their distances to the sun are proportional. In its simplest form, the orbital period is measured in Earth years, and the planet's distance to the sun is expressed in terms of the Earth's mean, or average distance to the sun in AU, which we call astronomical units. 1 AU is about 93 million miles, or 150 million kilometers. So Kepler's third law states that the planet's orbital period squared is equal to that of the distance cubed. So it can be most simply put as t squared equals d cubed. So we can say that the closer the planet that's orbiting the sun is going to have a shorter orbital period. And the further, the greater the amount of time it takes to orbit. So here's a quick summary of Kepler's laws. And we can show the numbers. The greater the distance a planet is located from the sun, the greater the amount of time it takes to orbit. Whereas Mercury is a very short distance, less than 1 AU. It takes a lot less time to orbit or revolve around the sun. And therefore, the greater the distance in AUs, or any distance, the greater the amount of time it takes. So that paved the way for Galileo Galilei. Galileo was a great Italian scientist from the Renaissance. Galileo's greatest contribution were his descriptions of the behavior of moving objects, which derived from experimentation. All astronomical discoveries before Galileo were made without the aid of a telescope. In 1609, Galileo heard that a Dutch lens maker had devised a system of lenses to magnify objects. Without ever seeing a telescope, he constructed his own, where he could magnify objects 3 times the size by the naked eye. And he was able to study, and he went about studying Jupiter and Jupiter's moons. So you can read these 5 here and make sure you're able to take notes. You'll be expected to know what those are. But really, Galileo, later, by even studying the sun, which later blinded him, he was able to determine not only planets, but also all objects in all kinds of different motions by direct observations that were supported in the math. And lastly, Sir Isaac Newton. He changed the game. He was able to not only come up with his 3 laws of motion, but I think as important as anything is his universal law of gravitation. That he was able to calculate the force of gravity between 2 masses at a distance that completely revolutionized the astronomical world altogether.